How's it going, everyone? Because of the fair today, like I talked about in the teams, we're just going to do recording, and I'll post the PDF of the blank so you can follow along. And I'm pretty much just going to be working through problems and explaining my thought process. If you have any questions, feel free to message me separately or leave them in the chat. And yeah, let's get into it. As you can see, I wrote down some of the important equations from this chapter here, as well as conversion here. So firstly, we have change in internal energy, and that'll be Q plus W, where Q is heat flow and W is work. And then we have over here, work is equal to the negative pressure times the change in volume. And Q equals the mass times the specific heat capacity times the change in temperature. And that change in temperature is always final temperature minus initial temperature. And then the last equation over here, we have delta H of the reaction, so the change in enthalpy for the reaction. Heat flow and enthalpy are very similar concepts. It's just a change in energy, but when you're talking about enthalpy, it's for a reaction, while heat flow is more generic. And this delta H, or change in enthalpy, will be the heat flow of the reaction divided by the moles. Okay, all right. So let's get into some problems, and you'll see how these equations work over time. So this first one says, calculate the change in internal energy for a system that has 501 joules of work done and transfers 300 or 3.7 kilojoules of heat to the surroundings. All right. A big thing when doing these type of problems, as you can, well, firstly, I guess, as you can see, we're trying to find the change in internal energy, which we know is Q plus W. And this isn't a very difficult equation, but the big problem is knowing your sign. It says work done and transfers heat to the surroundings. So let me draw a little diagram. We'll make this the system, and over here we'll have a work, and over here we'll have heat flow. So whenever work is being done to the system is gaining energy, so that sign is going to be positive. When the system is doing work, the system is losing energy, so the sign will be negative. When the system gives out heat, it's losing energy, and when it takes in heat, it's gaining, so it's going to be positive. All right. And so here we want to find the change in internal energy, which will be in units of joules or kilojoules. And we have 501 as our 501 joules will be our W. So our work done. But that's work being done. Oh, done on it. So that'll be positive. Right, the system has work being done on it. If we look at our little thing here, you'll see that that means it is positive. Okay, and now transfers 3.7 kilojoules of heat to the surroundings. If it's transferring, then Q is going to be negative. It'll be negative 3.7 kilojoules. All right, so there's our variables. And we want to find delta E, or change in internal energy. So one thing you'll notice is that, sorry, being distracted. One thing you'll notice is that we have a difference in units here. We have kilojoules and we have joules. When you're adding, you want the units always to be the same. So in this scenario, you're going to want to change them both to joules or both to kilojoules. Let's see if the problem specifies. The problem does not specify. So we can go ahead and do 501 joules, and we'll change, we'll just change Q to joules. So negative 3.7 kilojoules. For 1 kilojoule, you have 1 times 10 to the 3 joules. And if I get my calculator here, or actually in this one, you can kind of just do it with your head. You can see that it's negative 3,700 joules. Okay. And now we will come over here and we will add that, actually we'll subtract that negative 3,700 joules. And now I'll grab my calculator. Well, 501 minus 3,700 gives us negative 3,199 joules, or negative 3.199 kilojoules. Okay. And a big thing about these problems is just to look at that sign. It says, or we're looking for the change in internal energy, and we see that it's a negative. So intuitively, we can think about that and say that the system is giving off energy. The change, wait. Yeah. So the system is having an overall negative change in energy. So the system is giving off energy. We'll talk more about that in a little bit. Okay, let's move on to the next one. So for the next one, first let's read the question. We see that we have a gas expand from 5.80 liters to 10.53 liters. Sorry, I keep on getting notifications from Teams. I don't know why. Okay. All right, the gas expands from 5.80 liters to 10.53 liters. And so that's going to be our delta V, right? Our change in volume. And we know that we have to do final minus initial. So we're going to do 10.53 liters minus 5.80 liters. And that'll give us 4.73 liters. Okay, and now if we keep reading, we'll see that it has a constant pressure of 1.30 atm. So that'll be our P, 1.30 atm. And now we're here to try to calculate the work done, right? We want to calculate the work done, and then we want to talk about, is it done by the gas or to the gas? So we'll talk about that. Firstly, if we want to calculate work, let's look back at our equations. It's a negative pressure times the change in volume. So that'll be negative 1.30 atm times 4.73 liters. But will that give us, well, I mean, it will give us our work done. But the issue is, if you do this, and actually let me just erase this to prove this point. you'll end up with some answer ATM liter. And in this class, we prefer, and while that is a work unit, we prefer our answer to be in joules. So if you look back at the front page, it says 1L ATM equals 101.3 joules. So 1L ATM, 101.3 joules. I don't know why there is a meeting being started. Okay. So now let's put this into our calculator and see what we get our answer in joules, and then we'll talk about the sign convention, right? You can see here that it should be a negative answer, and it will be, but we'll talk about what that means. All right, so I just put it all on my calculator, and I got negative 622.89 joules. So that was our answer. Oops. And let's talk about the sign. So the sign is negative, and we want to know, is the work done by the gas or to the gas? So this original problem is the gas is expanding, right? And when this gas is expanding, it seems that there is negative work being done. And so what that means is that the work is done by the gas, right? The system is losing energy, therefore the gas is doing work to lose energy. So system slash gas is doing work. Okay, so that answers that full question. Let me go ahead and let them know to stop creating meetings. Or if I started a meeting somehow, I'm not sure. Okay. Sorry about that. Okay, let's talk about the next one. So, and let me see, can I see the length of this video so far? I'm not sure, that's okay. I'll just keep moving along a little bit quicker. This next question says, a certain reaction is performed under a constant pressure of 825 torr, pressure of 825 torr, and it gives off 5.25 kilojoules of heat. There we go. It gives off 5.25 kilojoules of heat. Okay, so that'll be our P. All right, and this will be our Q. But it says the system gives off 5.25 kilojoules of heat, so we know that needs to be negative. 25 kilojoules. And let's not change it to joules just yet to see what we need in the problem. Now, during the reaction, the volume expands from 5 liters to 43.25 liters. So final minus initial. Our delta V should be 43.25 minus 5, 38.25 liters. And that was right here. Okay, and now we want to calculate the change in internal energy again for the reaction. So let's see what we got. Change in internal energy we know is Q plus W. And we're given Q, but we're not given W this time. And that's because, just like above, W equals negative P delta V. So our equation can be expanded to Q minus P delta V. All right, so now let's plug in. And I think, and I'll explain why in a second, it would be best to change this to joules. So do 1 kilojoule here, and we'll do 1 times 10 to the 3 joules up here. All right, so let me go ahead and do that real quick. Negative 5.25. Well, actually, you can do that in your head. But it'll be negative 5 to 50 joules. Minus, and let me put some parentheses, P, which we said was, oh, we actually have to calculate that. 825 divided by 760, that's 1.086 ATM. 1.086 delta V, 38.25 liters. And the reason I changed this to joules is because I'm going to change this side to joules. Just like above, we're going to use that, because this is LATM, we're going to use 1 LATM equals 101.3 joules. And now we can subtract those. And let's see what answer we get. That was horrible. All right. 1.086 times 38.25 times 101.3. And I will do negative 5 to 50 minus that answer. And I got negative 9457.95 joules. Or, that would be, wait, sorry, clicking the wrong buttons here. Negative 9.46 kilojoules. So there's our answer. And how much we got left? Not too much. Let's move on to the next one. Calculate the heat flow Q. So we're looking for Q when 27 grams of iron is cooled from 71.6 to 24.3. And then it gives us the specific heat capacity of iron. Okay. So looking at our variables here, firstly we're trying to find Q. We're given M. We're given delta T. Oh, by the way, I should mention this. When finding delta T, I'm going to prove to you that it doesn't matter whether it's in Kelvin or Celsius. Yeah, I'll do it down there. Okay, so delta T is final minus initial. And I'm going to actually change those values to Kelvin because we've done Kelvin for everything. This entire year, we've never actually used Celsius. And so it feels very weird for someone to tell you that you can just go ahead and use Celsius now. But I will prove to you why. Okay, so now let me find that difference. And when I find that difference, you'll see that both of these actually equal negative 47.3 Kelvin or Celsius. And so it doesn't actually matter because it's a difference, and because down here you're just going to add to 73.15 to both of them. When you subtract, it just gets canceled out in the end, so it doesn't really matter. So because it's a difference, it doesn't actually matter what the units are for delta T. And because of that, actually, you can change this here per gram Kelvin to per gram Celsius, and the number will not change at all. It doesn't matter either way. Okay, let's move on. So we just found delta T. I took up a ton of space, and I can actually reuse this over here. See that C, or specific heat capacity, as shown in this equation here, where C is specific heat capacity, is 0.450 joule per gram Celsius, or Kelvin. So now let's find Q, because that's what we're looking for. All right, so Q equals MC delta T, or MCAT, as most people call it. And let's plug in our numbers. All right. Times delta T. And you'll probably have noticed that our answer is actually going to be negative. And that makes sense, right? It's cooling, meaning, yeah. So if this is getting colder, that means it's giving out heat. And when a system is giving out heat, it's going to be negative heat flow. Okay, so let me put this in the calculator. Right, you can look at this as well. A system is giving out heat or cooling down. The sign was negative. This is actually a pretty good little diagram. I would keep it handy. 0.450 times negative 47.3. And I'm getting negative 574.69 or 695. And let me double check my answer. Yep, I think this is actually the correct sig figs here. And that would be in joules. Nice. All right, next one. When 9.98 kilojoules of heat are added, so I'm just going to go ahead and mark down that that's positive, to 50 grams of an unknown liquid, the temperature from the liquid rose 37.5 to 120. What is the specific heat capacity of the unknown liquid? Very similar to the last one. So let's run through it. Q equals positive 9.98 kilojoules. We can go ahead and convert that immediately. Okay. Mass equals 50.0 grams of an unknown liquid. And the delta T is going to be final minus initial. (82.5 degrees Celsius). And let's go ahead and change this. 9980 joules. And now we're looking for specific heat capacity. So if Q equals MCAT, then specific heat capacity is going to be Q over M delta T. All right, so let's plug in all of our numbers, which was 9980 joules over 50 grams times 82.5 degrees Celsius, and C equals, let's see, 980 divided by 50 divided by 82.5, and I'm getting a specific heat capacity of 2.42 joule per gram, that looks like grams, joule per gram Celsius. Not bad. All right, how many more? We have 1, 2, 4 more. We have a chunk of iron with a mass of 82.9 grams. It absorbs 4.10 kilojoules of heat. The iron's original temperature is 25 degrees Celsius. Ooh, nice. What is the final temperature of the iron? And it gives us the specific heat of iron. Let's mark down our variables really quickly. Mass equals 82.9 grams. Q equals absorbs, so it's positive, right? 4.10 kilojoules. Let's just change it to joules. Joules, okay. And the iron's original temperature, so I'm going to mark it TI, is 25 degrees Celsius. What is the final temperature? And C is 0.450 joule per gram Kelvin, but I'm going to change it to Celsius because that's what we're using. Okay, so Q equals MCAT. Now, when we're looking for the final temperature, there's 2 ways you can do this problem. First, you can solve for delta T and then expand delta T, because we know that delta T equals T final minus T initial. Or, sorry, I need a drink. Or you can just plug in TF minus TI right now into this equation. I think we should just solve for delta T first, so we have less variables to deal with at one time. So let's go ahead and do that. Q over MC equals delta T. And make sure these units match, joules and joules, and they do. 82.9 and 0.450. Excuse me. Let's put that in and solve for delta T. And I'm getting 109.9 degrees Celsius, and that's going to equal our delta T. But now, 109.9 Celsius equals our delta T, but that equals T final minus T initial. And we were actually given T initial. So 109.9 degrees Celsius. And I'm just going to go ahead and add this over because we're looking for the temperature final. Plus 25 degrees Celsius equals T final. And I got 134.9 degrees Celsius. Let me double check. Yep, that's exactly what I got last time as well. Okay. Not bad, a little more challenging than these ones before. Kind of scaling in difficulty as we go on. And that'll be more apparent with these next two. Okay, so here's a more challenging one. This one I would say is pretty important because this one right here is likely to be a challenge problem on your exam. So I would definitely go ahead and pay attention to this one. Okay, piece of copper has a mass of 237 grams, heated to 100 degrees Celsius. Then it is placed in 100 grams of water at 25 degrees Celsius. What is the final temperature of the copper water mixture? Assuming that no heat is lost to the surroundings. Okay. And it gives us the specific heat capacity of copper, but also the specific heat capacity of water. Okay, so that's everything it gives us. I'm going to go ahead and move all these variables to the next page because of the way GoodNotes works. Okay, so we were given mass of copper. Okay, and then it says, yeah, so there's our mass of copper. And it says that it was heated to 100 degrees Celsius and then placed in 100 grams of water at 25 degrees Celsius. So in this scenario, you know what? Let me draw a picture. I think that'll be better to explain it. Imagine we have a beaker here, and it's full of water. And we have this piece of copper, and this piece of copper is 100 degrees Celsius, right? And now I go ahead and I put that into water, but this water is 25 degrees Celsius. And when I put that copper in the water, there is a specific temperature that that copper is going to change to. If you know about thermal equilibrium, you'll know that that 100 degree copper will change to 25 degrees Celsius of the water. Right, they're going to equal out, wait, actually, no. We'll come back to this, but it won't change to 25 degrees Celsius. Sorry if I caused any confusion. So instead, let's write down here, it said the copper was heated to 100 degrees Celsius. So we're going to go ahead and call that T initial of the copper, right? It starts at 100 degrees Celsius. That's T initial copper. Okay. Sorry for the confusion with going to the diagram. I'll get back to that later. And now we have 100 grams of water. H2O, 100 grams. And the T initial for the water is 25 degrees Celsius. Okay. And the final temperature is what we're looking for. Now, this is what I was trying to get to earlier. So the water starts at 25 degrees Celsius, but it doesn't end at 25 degrees Celsius. Same with the copper. It starts at 100 degrees Celsius, and it's going to change to another temperature when we put it in that water. But the thing that you need to know here is that the T final of the copper is equal to the T final of the water due to thermal equilibrium, right? If you take your hand and it's kind of cold and you place it on a surface that feels warm, if you leave it there for long enough, your hand is going to stop feeling warm or cold. It's going to feel neutral because it's going to be the same temperature as the thing you're touching over time. Once that heat transfers back and forth, you'll reach thermal equilibrium and they'll be the same temperature. So the T final for the copper and the T final for the water are equal to each other. And that's actually what we're trying to find, is the final temperature. So instead of having a specific T final of copper and T final of water, we're just going to have a T final. And is that everything we need? No, it's not. Specific heat capacity of copper is 0.387. Okay. And for H2O, it is 4.18 joule per gram. I'm actually going to do Celsius. And now that's everything we need. So you'll notice something here is that we have everything we need besides the T final and the Q to set up an MCAT equation. All right, we're just missing Q, and if you expand this into T final minus T initial, we're missing the T final. But we have it in two different substances, which kind of makes things confusing, because which ones do we use? And the way we can do this is, let's think about it like this. Earlier I said through thermal equilibrium, the copper and the water are going to share their heat until they reach equilibrium. So that means that they're transferring the same amount of energy to each other. It means that the heat flow of the copper is equal to the heat flow of the water. They're both putting equal energy into each other to balance out. However, we can't leave this equation I just created like that, because we have to give one of them a negative sign. And mathematically, it really doesn't matter which one you give it, but if we want to actually be correct, it would be the copper, right? The copper is giving out energy, or the copper is giving energy to the water. But the water is taking in energy from the copper until they even out. So the heat flow of the water is going to be positive because it's gaining heat, and the heat flow of the copper will be negative because it's losing heat. So let's move that equation over. All right, and Q equals MCAT, right? So we can expand this to be mass of copper times the specific heat capacity, T final minus T initial copper equals the mass H2O, specific heat capacity H2O, T final minus T initial H2O. Sorry about the bad handwriting. Okay, and once we're at this, we can actually go ahead and plug in. So we can say that the mass of the copper, 237. Make sure you're checking your units, by the way. Nope, it's incorrect. 0.387. T final minus T initial, which in this situation will be 100, equals 100 times 4.18 minus 25. So that's all of our variables. And now we just have to do a bunch of algebra. So we can combine these together and distribute it. Combine these and distribute it as well. So let's do that algebra together. Give 9. Oh. Okay, plus 91 or 917 point. Oh, sorry. There's a massive glare on my calculator. I cannot see the decimal points. Okay. Now we need to add like terms. Negative 91.719 plus 418. That'll give us 326.281 TF. And now let me, oh wait, I actually made a Very simple algebra mistake. I just added those numbers together, but we actually, well, yeah, that's fine. You know what, we can just add them together. So I'm going to add 91.719 to this side, and I'm going to add this to the other side. Don't make simple algebra mistakes. Okay, now we need to divide. Okay. And let me divide over and see what we get. T final equals 38.4. I'm actually just going to do 0.5 degrees Celsius. And let me double check with what I had gotten previously. Sorry, it kicked me out of my key to double check everything. All right, let's see. Yep, that is what I got last time, which means we made no mistakes in our algebra and we set up our equations correctly, and that would be how you solve a problem like this. Just, you know, this is a problem where you have to kind of use some intuition here to make this equation. After time, it becomes second nature. And you also have to understand some thermal equilibrium, but not too bad overall. Just take some practice. And we actually have one more very similar. I'm not really sure how long this recording is at this point. I don't think it's too long, but it's nearing 30 minutes. I know that the longer the video, the less likely anyone is to watch it, so I'm going to try to hurry up. But let's take a look. When 5 grams of barium oxide is placed in 100 grams of water at 25 degrees Celsius, the temperature of the resulting solution increases to 37.2 degrees Celsius. Given the specific heat capacity of the solution is 4.18 joule per gram Kelvin, so most likely water, and assuming no heat is lost to the surroundings, determine the delta H for the reaction in units of kilojoule per mole of barium oxide. Okay, so that's important. So here's our equation, and let's write down some variables. So the mass of barium oxide is 5 grams. The mass of the water is 100 grams. And so we can kind of think about it like this again, just to have an intuitive understanding. We're putting this 5 grams of barium oxide into some water, and it's forming this solution. So this whole thing here is our solution, just some barium oxide in some water. Okay. And it says that it is at 25 degrees Celsius. We'll talk about that a little more to see where we want to put that first. Let's keep reading. And then the temperature of the resulting solution increases to 37.2. Okay, so now we can be sure that since the temperature is increasing, we know for sure that our T initial is going to be 25 degrees Celsius, and our T final is going to be 37.2 degrees Celsius. And the specific heat of the solution is going to be 4.18 joule per gram Celsius. Okay. So we want to find delta H of the reaction. And we know from the front page that delta H of the reaction is Q of the reaction over N. Okay. And we want it in units of kilojoule per mole barium oxide. So we know that this needs to be moles of barium oxide specifically. Right, so we're finding the energy, the change in energy per mole of barium oxide over here. Sorry, man. There we go. But to do so, we're going to need Q of the reaction. And the only way we can find that Q of the reaction is by a similar equation to last time. So when this 5 grams is placed in 100 grams of water, it's at 25 degrees Celsius. And the temperature increases for the solution. So if the temperature of the solution increases, you could say that its energy flow is positive. But that energy has to be coming from somewhere, and it's coming from the reaction, right? And the reaction is just putting barium oxide on water. And so Q of the reaction is positive Q of the solution. And we want to find Q of the reaction. So I'm actually going to move that negative over, because mathematically it doesn't really matter. We just want to solve. And we could say that negative M of the solution times C of the solution times delta T, well, I'll just do final minus initial. Final minus initial for the solution. And it's T, F, and Ti are simple because they're just kind of given to us, right? It's at 25 degrees, then we put it in, and now it's at 37.2 degrees, so that works for the solution. And it also gives us C of the solution, which is nice and simple. However, the complicated, and it's really not too complicated, is mass of the solution. So we're given the mass of the two things in the reaction. So if you just add those together, we'll have the mass of the solution. So with 5 grams plus 100 grams, it's just going to be 105 grams is our mass of the solution. So negative 105 grams times 4.18. And now we'll do, since it increases, it's final minus initial. Well, it's always final minus initial. But since it's increasing, we're going to have a positive. So we'll solve for Q of the reaction. Let's see what we get. We get negative 5354.58, and the units of this will be in joules, because right there, our specific heat in its units of joules is in units of joules, so our heat flow is going to be in units of joules. So now we have that, but we wanted delta H of the reaction, so we're going to plug in negative 5354.58 joules over the moles of barium oxide. And in this scenario, how many moles of barium oxide do we have? A mistake you could make would be putting 1, because there's 1 mole there. But we're actually given 5 grams. That was horrible. 5 grams of barium oxide. And so we're actually going to need to do some stoichiometry. So let's do that real quick. The molar mass of barium oxide is 153.3 grams per 1 mole. BAO. And I don't know what that comes out to. But if you do that stoichiometry, you divide it by our heat flow, you're going to end up with negative 164. Let me put it in real quick again. I think I made a mistake. Okay, I fixed it. 171.42 joules per mole barium oxide. And I just realized it wanted kilojoules, didn't it? So I just did some extra stuff for no reason. But luckily, you can just move that decimal place. That'll be per moles of barium oxide. And there's your answer. And that is delta H of the reaction. There we go. And now the last one. The last one is actually pretty simple. So here it gives us, it gives us our reaction and it asks us to calculate the change in heat content when 15.5 grams of iron reacts with excess of oxygen. And then it asks, is this heat absorbed or released? So there's an extra part to this question. So let's look at this. So it gives us 15.5 grams of Fe. Wants to know the heat content or the heat flow for this. Now, we don't know this, but we do know the heat flow for 4 mole of Fe. So when there's 4 mole of Fe, this is the heat flow, or the, well, I guess, sorry, I should stop saying heat flow and say enthalpy, the enthalpy of the reaction. And so, and I'll just write this down and then I'll explain further. If we wanted, or not if we wanted, if we did change this to moles of Fe, we could actually use this in our stoichiometry. Because when we have 15.5 grams of Fe, and we know this is per 4 mole of Fe, if we get to moles, then we can use that relationship of 4 moles to Fe to our enthalpy reaction here to cancel out moles and get us in units of kilojoules. And this will actually give us the heat flow, or sorry, the enthalpy reaction for 15.5 grams of Fe specifically. And it asks us to talk about whether it's absorbed or released. And it is a negative, and so if delta H here is negative, then that means heat is released, right? It's giving out energy or giving out heat. So this is giving out heat slash energy. And so that's what our negative means here. So it is being released. Okay, that's everything. If you have any questions over any of this, please feel free to ask me separately or in the Teams chat. I know this is a little different than normal, and I hope that it's useful. After I post this, I will follow up with the blank PDF for you to print out or just follow along, whatever you want to do. Thanks for watching. Hope you guys had a great fair.